I pull all these to the other matrix over here. Of course, it's all equal to 0. And then what? Then I have that partial g partial x is all this. But the thing is, you notice that you've got the same derivative function each place here, right? So lo and behold, we get that partial g partial x times the partial g partial y matrix times this matrix of derivatives of our solution, our implicit solution, is equal to 0, which then finally gives me that the rule for the derivative of the implicit solution is simply to multiply the inverse of the Jacobian with respect to the variables you're solving for by the rest of the Jacobian derivative with respect to the independent variables. And so that is a follow-up to the solution techniques. It tells us not only is there a solution, we can write the derivatives of that solution in terms of these same matrices in this way. Yeah.
Is that G inverse the G inverse that that converges to?
No, that is G inverse. That is the inverse of the Jacobian. So G is given. Different G. So in this first part of the lecture, we were finding a G to be the inverse of the function. Here, G is the name for the system of equations we're solving. So we're not. This is a given G. It's not a found G. Yeah. So we're literally just differentiating that given set of equations with respect to the n variables y1 through yn. That gives us an n by n matrix. We can invert it. All right. Anyway, so this is the implicit function theorem. Basically says that you can do what we just described, and if you keep doing it like this, that sequence converges to the implicit solution, which is in fact continuously differentiable with the derivatives described by the box that I have right there. Now, the proof here, I won't show you except to do this. I'm only going to show you that much, but I will summarize it, which is to say that that proof is simply to invent a mapping and then use the inverse mapping theorem to prove the implicit function theorem. Because you can, if you get one, you can prove the other if you're a little bit creative. That's what that proof is. So I talked to you guys about solving the circle. How about solving the sphere? If we have x squared plus y squared plus z squared equals to a constant in 3 dimensions, then one equation, 3 unknowns. That means we're looking at a 2-dimensional thing, so we can solve for one of the Cartesian variables in terms of the remaining 2, locally, right? When can I do that? Well, here the Jacobian is just got 3 components, gx, gy, gz, and so if gz is not equal to 0, you can do this, you can do that, you can do that, simple as, right? So the implicit mapping theorem is extremely simple in the context of just like one equation. We just look at partial derivatives with respect to the variables. If the partial derivative is non-zero with respect to that variable, we can solve for the remaining ones. That's the easiest version of this theorem, all right? By the way, if you think back, if you think back to Calculus 1, you're minding your business, you did limits, you were happy they ended, right? Limit laws were passed, the definition derivative was behind you, you're finally starting to do the power rule. Yay, everything's happy, right? Yeah. And then, all of a sudden, the professor starts implicit differentiation, and you're like, what's this, right? I mean, what's this? But you should have stopped and asked him a question that none of you did, but you should have asked him this question. Dude, you never proved y is a function of x. You have this equation that intertwangles y and x. You differentiate, you assume y is a function of x. Why can you do that? No one ever proves this. We just differentiate. We assume y is a function of x, and no one. You guys are just happy that we're not doing limits, so you don't question it. That's actually part of the reason of lecturing limits for 2 weeks. Is to depress you from asking the questions that you should ask, because you're afraid it might bring you back into limits, right? That's my theory. But the answer ultimately, though, is that the motivation for implicit differentiation is the implicit function theorem. You actually need advanced calculus to prove that there exists a y which is differentiable that you could solve for. And you can generally only do it locally, right? You actually need the partial derivative with respect to y of that defining equation is non-zero at the point you're solving for y. Otherwise, you can't write y as a function. Well, you don't have this condition to say you can. Maybe you can. Again, the implicit mapping theorem doesn't tell you absolutely what you can or can't do. It just tells you that that's a sufficient condition to solve locally for some of the variables in terms of the others. Oh, shut up. All right, so here's another one, x, y, z, trying to solve x plus y plus z equals to 2 and x plus y equals y plus z equal to 1. This is a system of linear equations. So now I'm not approximating when I do the Jacobian stuff, right? So my g is going from R3 to R2, right? R3 to R2. My solution set's not empty because I noticed that 101 maps to 21. Hooray. Here's my Jacobian. My Jacobian, sorry, I hope you guys don't mind. G prime is another notation for J sub G, all right? 1, 1, 1, 0, 1, 1. All right, so if I wanted to solve for x as a function of z and y as a function of z, I would need for the xy part of this matrix to be invertible, is it? Is this 2 by 2 matrix invertible? Well, yeah, it is, because these are not the same, they're not linear multiples of each other, right? For two vectors to be linearly dependent, you'd need them to be the same. Can I solve for x as a function of y and z? I cannot do that, you see, because the y-z columns, if I look at those as a 2 by 2 matrix, that's not invertible because the columns are linearly dependent. If the columns are linear, if they have the same column, it can't invert it. The determinant of this piece is 0. So this partial g of xy is this, which is invertible, so I could solve for z as a function of x and y. But on the flip side, I simply cannot solve for x as a function of y and z. All right, you can't do that. And if you put this together, if you put the defining equations together, it gives you like x equals to 1 on the line of intersection. So we can't really use x as a free variable if it's fixed to be 1 along the line of intersection. That's why the implicit mapping theorem doesn't work out. Again, I shouldn't say what it doesn't say. The fact that the implicit mapping theorem's conditions are violated doesn't necessarily mean that you cannot solve for x as a function of y and z in the abstract. However, for this example, it is true that you cannot solve for x and z. So you cannot solve for x as a function of y and z because of the algebra right here. Not because of the theorem, but because the algebra shows you that literally you can't do it because x is identically equal to 1. So, all right. Next example, we have from R4 to, how many we got here? 1, 2. So I'm going from 4 free variables to 2. So 2 equations and 4 unknowns. So I expect that I'm looking at a 2-dimensional object. All right? So the Jacobian here is this. All right? And let's see here, what do I do? Oh, minus 1, 3. Now these are linear equations, so I can use techniques of linear algebra to solve for it. I calculate the row-reduced system of this equation. I get this, and that reveals to me that the general solution set has the form, x equals to minus u plus 2v plus 7, or y is equal to 2u minus 3v minus 11. Apparently, we can make x, y to depend on uv if we wish. This is a standard calculation. So we can solve this 2 equations and 4 unknowns for x and y. What is it?
What does an I do?
That? That's a cursor. Curse the cursor. There you go. What's that arrow doing there? Nice follow-up. I like it. All right. Now, check it out, though. What if we switch the order of the variables around? So instead of doing x, y, u, v, what if I did u, v, x, y? Well, I can still use linear algebra to solve it. I just do the row reduction, and I get this. So, oh, hey, apparently I can also write u and v as functions of x and y, as is evident from this. All right? But notice also that if you just go back up and look at this matrix, we could have anticipated that. See, because this is the part of the Jacobian. That's the xy part, right? So it's invertible, which means I can solve for x and y in terms of the remaining variables. This part of the Jacobian is the uv part. So of course I can invert, it's invertible because it's determinant's 1. So I could solve for u and v in terms of the remaining variables. Let's see here, anything else? How about, I'm trying to see if there's anything I can't do. I'm assuming I probably made it so there's something I can't do going on. Let's see. X, if I solve, did you say backflip? Is that what you said? Fair. Not in this gravity. So yeah, where was I? Oh man, completely derailed. I'm going on. It's a good example. It was a good example. You're not sorry.
Can you solve for x and u? Maybe remember it.
I think maybe it's possible to solve for any two of those variables in terms of the remaining two, because it ultimately rests on the question, if I pick any two columns in the Jacobian, if those two columns are not multiples of one another, then you can solve for those two variables in terms of the other two that remain. I think it so happens that it's possible there.
Use a wedge product for that?
You could use the wedge product, yes.
Does it have to be, you have to do REF to determine that, or can you just determine it by
You can use the implicit mapping theorem, just look at the columns that correspond to the variables you're solving for. But to actually find the solutions, you could use the REF. See, linear algebra gives you a method to find the solution set. The implicit mapping theorem doesn't tell you how to find the solution, it just tells you it exists. And it gives you a roadmap for how to calculate the derivatives. This one here, we've got 5 variables and 3 equations, right? So 5 minus 3, so we expect to be able to solve for two of the variables in terms of the remaining 3. No, wait a minute. 3 of the variables in terms of the remaining 2, right? So, yes. Okay, so here's the Jacobian. Great. And if we go on here, I can solve for this. I can look for x and y and z as functions of a and b. And here actually is straight up the linearization of that system of equations using the Jacobian. All right? There is, you could teach linear algebra with this. I never have, but this actually is a method of calculation. I don't know. Okay, so notational chimera explicit. It's a mix of things. So it's like a yeah. Did I tell you guys about the future ruler of Mars? Elon Musk. Did you just guess that?
Yeah.
So in the late 1940s or early 1950s, Werner von Braun, the famous Nazi scientist who came and became the founder of our liquid fueled missiles, he wrote a science fiction book about a technocracy being founded on Mars, where there would be a ruling council of 10, the leader of which would be called the Elon.
What?
True story. Yes, I read it in an article this week. My mom said she heard it a year ago. So, but anyway, my mom is more well-read than I am. Anyway, so the point here is I can actually solve for x, y. This matrix is invertible. I have not shown the calculation. This is like using technology, okay? But the inverse of this matrix is that. So I can solve for this by multiplying by the inverse of this matrix, and out pops this equation. That actually is the solution set for x and y and z as function of a and b. Just like that. So there's the solution. Now I guess the question, is it possible to solve for any triple of variables of x, y, z, a, b for that given system? In fact, no. If, let's see here. Oh, so here I use the column correspondence property. So if you calculate the row reduction like that, what this means is that, let's see here. The third, this fourth column is going to be the sum of the second and the third. Try this out. If I take column 2 and 3 and I add them, I get the fourth column. See that? 2 plus 1, 3, 2, 2. What that means is if I just look at that 3 by 3 matrix, it will not be invertible because one of the columns is a linear combination of the others. The determinant of that middle matrix is 0, which means I cannot solve for these 3 variables in terms of those 2. Right? That's impossible. Because of linear algebra, it's also where the implicit function theorem is going to fail. Here's the actual matrices for those other selections of variables. All right. So, I should mention that all of this has been for independent constraints. If the given set of equations was redundant, everything we're doing kind of breaks down. So like for this, I mean, I guess we've been assuming that there exists an invertible matrix, right? So like, if it wasn't possible to select some subset of variables for which the Jacobian was invertible, that would speak to the fact that the given set of equations was not really independent. You've got some kind of duplication, and that's a harder problem. And I really address that at the end of the chapter in terms of what's called the constant rank theorem. So if you look at the end past here, oh man, did I get rid of that? Oh no, it's right there. So the constant rank theorem basically says that if you look at the Jacobian and its rank is k, what that means is if you look at the mapping, it is going to give you an image. The whatever it maps to has basically k-dimensional locally. And what is rank? Well, rank is the number of linearly independent columns in your Jacobian matrix. That's what the rank of the map is. So, and I've got like 10 examples to illustrate the idea, but I don't think I really have any homework problems on this, but I do have homework problems on the previous thing I just skipped past, which.
Oh, it is Hibner. Wait.
What's that?
I said Hibner when you were scrolling by it, but then I just saw ideal gas. It really is Hibner.
Yeah, we'll talk about that. So I think I'm out of time for today, but when we come back next time, I will explain to you guys how we do partial differentiation for more than, like, so here's the fundamental question. You've got like a system of equations and you're trying to calculate derivatives of some variables in terms of others, right? If you think about it, you could choose, there's lots of different choices you could make. If I've got like 2 equations and 5 variables, that means I can write 3 of the other variables as functions of the remaining 2. Well, which ones do I choose to be, the dependent? Which ones do I choose to be the independent? And then the question is, how do the derivatives of those variables with respect to the other variables interrelate? All of these questions are answered ultimately by a very simple procedure, which I'll show you next time, which is we just simply take the system of equations and we take the differential of all the equations, and all you have to do is solve for the differentials of the variables that you want to be the dependent variables. You solve for those in terms of the differentials of the independent variables, and from that you can read off the derivatives of everything involved. So it's almost like what I did today in terms of like you just take the differential equation and take the equation rather, differentiate it, you'll find an equation involving differentials, and from that you can read all of the partial derivatives that you want to. And anyway, so it takes me at least half hour to explain that. I'm not going to do it today. So my apologies. I seem to be slightly behind, but we'll catch up next class. So. Thanks, guys.
Thanks.